Today I'm going to talk about knotting surfaces in full manifold by some surgery. So let me write down the title first. Yeah, this is a joint work. Then your Ruberman. Okay, so in four-dimensional topology, people talk about exotic smooth structure. So what do you mean by this? Well, usually people think about construction of full manifold, which is non-diffeomorphic, but all homeomorphic. Then we call that's the exotic full manifold here. So this thing actually developed by the cyber-weapon theory and also gauge theory. And we can ask such a question also, relative version for surface case. So construction of surfaces in a fixed full manifold. That are topologically all equivalent, but not smoothly. So you might ask about the group action also, such a question, exotic group action in full manifold theory. But also in this talk, I'm going to concentrate on this topic. That's the main question in this talk. So let me write down the problem again. So if you have a full manifold, smooth full manifold, usually we always assume that that's the closed full manifold. When you have a surface, embedded surface in there, then you might think about, you might change the embedding of surface again here. So you will get the new surface, sigma prime. Then this sigma is pairwise homeomorphic. But not diffeomorphic. Then we call such a surfaces we call sometimes exotic surface. So smoothly knotted surface, but this is topologically standard. Then we have to think about what operation can change the embedding over here. So, well, here we use some surgery along with some torus. So if you have, if this is the ambient space has some torus, if you do some surgery along that torus, you might change the embedding of surface. Why it happens like this? Maybe you can see the analog in three-dimensional case also. So here I think the chi-state is very strong and not theory. So probably maybe it's is that?
I think I'm the only one.
Is it?
What happened to all these not theories?
What happened? I thought there are many not theorists and chi-state. Maybe my plan was wrong.
No, there are many. Yeah, they are all sleeping now.
Okay. too. Let's do that then. So let's consider some ONNOT in S3. As you can see, this is an ONNOT. Is it ONNOT, right? And then maybe you can think about torus here. We take out this torus, and then we glue another torus. Here the gluing map, this meridian goes to one longitude, one meridian, like that. Then this is actually blow up. That's the +1, something like that. Then what happened to this knot? Well, some twist happened. That's the left twist. So it looks like this. So now you can see, according to this operation, you will get the new knot here.
If you are embedding this, why this you are, I don't understand this procedure. Why this?
Yeah, this is you can take out that it's a solid torus in here, and then glue another torus along the boundary there. So boundary is determined by where the image of so the image of this goes to the one longitude, one meridian. Then this one happens like twist happen on the knot. So we call this in three-dimensional case we call that a blow up. Then
I think you call this then surgery.
well, yeah, well. That's true. So Rifson twisting now is then surgery too. So that's true. Anyway, so that's the three-dimensional case. We can change the knot. So according to the surgery along some torus in there. So a similar thing happened in the four-dimensional case as well. So let me mention about some surgery, which is called knot surgery. So we call that's the knot surgery, which is developed by the Fintosh and Stone. They used a similar idea on the four-manifold case as well. So when you have a four-manifold, and then some torus is sitting there, let's suppose that, and then this torus has a trivial normal bond. So self-intersection is 0. But such a trivial torus is sitting here, then you can change the full manifold itself. So take out this torus, and then
Gamma is just the surface, so I just torus.
T, this is a torus. That's the torus, sorry. That's the torus. True. Yeah, thank you. Yeah, when you have such a torus in there, let's forget about the sigma first, the embedded surface now. Let's forget about that for a moment. So in that case, so take any knot in S3, like trefoil knot, something like that. Then we take out the exterior of a knot. Let's call that the exterior of a knot, and then times S1. So, and then glue together. So here this diffeomorphism could be any diffeomorphism defined on T3, which is the boundary of that, and then to the boundary of the exterior of a knot times S1. And then such that always here the normal disk, boundary of normal disk should be identified with a longitude. Yeah, this condition relates to some computation of cyber with invariant. So they fix this condition here. Then you will get some new manifold. Let's call that's the x of k. So they use this operation to construct some exotic full manifold. They used a lot of this tool. Yeah, so they get the interesting full manifold a lot though. So, and then they compute the ferromorphism type.
Excuse me, lambda K, what is P star? P star is it homology? Where?
Yeah, homology should be there. Homology class of the here the boundary of the normal disk should be the homology class to the longitude. Longitude. Yeah.
That's the longitude.
Yeah. Then, so you get the new manifold like this. So they compute the diffeomorphism type for this. So I mentioned like in the, just this cyber with the invariant. Cyber with the invariant is diffeomorphism invariant in full manifold. So to distinguish in a smooth structure of a full manifold, they always compute cyber with the invariant. So what's the difference of cyber with the invariant of new manifold and the original one? So interesting happen like, actually you have to be a little bit careful, but so just roughly speaking, just in the cyber with the invariant of this new manifold is cyber with the invariant of the original one times related to the Alexander polynomial of this. So here the t is, but I'm just roughly right here. So here t is, so related to the this here torus here. So this is Poincare dual of the, I use the same notation, but that's the homology class. Okay.
See exponential, what, 2 times t? 2
Yeah, 2 times the Poincare dual of the torus, which we used in surgery. Well, cyber
The Poincare dual is contained in cohomology, right?
yeah, cohomology.
What do you mean by exponential of that?
Well, we just in Alexander polynomial, t is, so it's gonna be t to the something, some polynomial like that. That's the actually t is exponential something 2 to the t. We use such a symbol as just in a t. Okay, so usually the cyber with the invariant is defined on the spin C structures on full manifold, but in this case, we have to transfer this. You have to translate this one as some polynomial form. So they use like some basic class, and then as they express cyber with invariant as some normal polynomial. So and then you just multiply by the some Alexander polynomial.
So this
Okay.
is now in the cohomology ring of this.
Exactly, yeah. So we have such a relation between the non-surged manifold and the original manifold. So then what can you do with this surgery for the surface says in full manifold? Later they,
I'm sorry.
yeah,
So you are taking exponential as a series expansion of this, and then you consider exponential as a series expansion.
right, yeah.
Okay. So you're
But the-
considering that as in the cohomology.
Yeah,
Cohomology.
cohomology. Yeah. So it's gonna be in the
So and then
H over 2
if
of
it is higher than the dimension of the manifold, so if it's higher than 4, then it is 0.
yeah.
So basically it gets truncated.
Yeah, that's true.
But can you do this also for high dimensional manifolds, or I mean?
Embedded is not defined.
Right. So
So
it
basically, it depends just on the Kesson invariant or something like this, not really on the whole Alexander polynomial.
right. Yeah. That's true. Okay, so now let's talk about the surface case again. So we are interested in some operation, surgery operation, to change the embedding of surfaces in full manifolds. So what can you do with this surgery? Well, Fintosh and Stone, later they realized this surgery can also change the embedding of surface without changing the ambient space. So how can you do that? Well, it depends on the choice of the torus and also choice of the this diffeomorphism. So here, if you choose well, like the good torus and then good diffeomorphism, then you can only change the embedding of surface without changing the ambient space. So let's call they actually called this is rim surgery. Rim surgery is a special case of a knot surgery. So let me describe what it is exactly. Let's take the simply connected four manifold. That's the simply connected four manifold, and then we have a embedded surface there. We only talk about the oriented surface, and then genus is positive. So that we just exclude the sphere case. Sphere case is actually the side with the invariant actually cannot distinguish their diffeomorphism types. So we just avoid that case. So, and then when you have that, so you have a embedded surface genus G like this. So what's the, we're gonna take some torus in there. To do that, take a non-separating curve alpha on the sigma. Then the neighborhood of alpha looks like just alpha times B3 ball. So here the B3 ball we can rewrite, that's the just I times D2. So the alpha times I, that's the annulus actually. The annulus is just nothing but the neighborhood of alpha on the sigma. So here as you can see, so annulus sitting here, that's the neighborhood of the curve alpha on sigma, and then times normal disk there. Okay, so we're gonna look at the that neighborhood again. So here the B3 ball containing this arc I times normal disk in there, and then times alpha direction. That's the neighborhood of alpha. So, and then take a knot, NS3. Remember we have to take some torus here to do some knot surgery. So we will take the torus like here, T is alpha times the meridian of the sigma. So meridian of this sigma. Actually, what's the meridian of this surface? Actually, that's the meridian of this arc, isn't it? So this is exactly, that's the mu sigma, that's the alpha direction. So it's sitting here, meridian of sigma inside ball, 3 ball, isn't it? Is that right? So, remember here, if we just take some curve on the surface, non-separating curve, and then that curve times meridian of that surface. So we take that torus.
Meridian here, it's what is meridian?
So here look at here the meridian of surface mu sigma is actually same as the meridian of this arc in B3 ball. Because remember, that's the B3 ball was, here I times D2, wasn't it? So I was the part of the surface, that's I. And then times normal disk, D2, that's the D2. So meridian of that sigma is, the isotopic to the boundary of this D2. So that's the meridian of surface, isn't it? Can you imagine that? Okay, and just remember.
Meridian makes me confusing. I cannot see the meridian there, but anyway, I
okay, so remember just the neighborhood of the curve is just annulus times normal disk, isn't it? That's a normal disk. Boundary of the normal disk should be meridian of the surface, isn't it? So that's why the meridian of that surface looks like the meridian of that's the normal disk sitting there. So that's the rim torus. So use such a rim torus and then do the knot surgery. What was the knot surgery? Where we take out that torus neighborhood and then glue with the exterior of a knot times S1 with some gluing map. So in this case, so what is the neighborhood of that torus? Well, that's actually sitting here in this ball. That's sitting here the alpha times mu sigma times here the disk sitting there. That's the neighborhood of that torus. Right? And then we take out that. That's the torus alpha times D2 glue with the exterior of a knot times S1. Again, the exterior of a knot. Remember, the exterior of a knot was just in here. Complement of should be the knot there. But here, let's consider this reason in the B3 ball again. So how can you do that? Well, S3 is a union of 2 3 balls. So here, we imagine that 1 3 ball containing knotted arc part. Then outside is another 3 ball containing trivial arc part. Okay, and then exterior of a knot is same as actually exterior of a knotted arc in B3 ball. So what? Okay, let's get here a little bit. Here B3 ball containing knotted arc. We imagine that knotted arc inside here. So take out the complement of the knotted arc. Okay, we can imagine there another part in here. So just in the neighborhood of this arc, just getting fat, and then imagine the whole thing is the neighborhood of this arc, right? And then just take out the knotted arc part. So that's actually same as exterior of a knot. Okay, so we just imagine that in the B3 ball complement take out this knotted arc. So now let's specify what's the gluing map here. Well, the gluing map is determined by the mode class. Remember that we have to glue this rim torus and then the boundary of the normal disk to the here. What's the boundary of this? The meridian of K and then S1 and then longitude of K. Here the very simple diffeomorphism we're going to take. Just this meridian of surface, identify with this one, identify with that. And then remember, this one is always should be identified with the longitude of the K. So that's just identity map on there. Then what is this operation? We have to think about. Well, I don't have to color chalk, but okay. Everything is yellow. Here. So here the operation was, remember just in here, that's the push off of the meridian of surface. This one is identified with the meridian of a knot, UK. So we just identified two things there. And then what's the here? That's the boundary of the D2 that is identified with the longitude. With this. And then alpha factor just identify with the, oh here that's one. We have to identify with that. Then what is this operation? Maybe, so you might notice that. So forget about this factor first. Just in this operation. Here here meridian is identified with the meridian. This normal disk here, the boundary is identified here, longitude of that. What is this operation? Well, this one is nothing but, so here the trivial arc, we're knotting the trivial arc in B3 bore. So that's this operation actually replaced by B3 bore and knotted arc. So what is this operation? Well, this is just knotting this trivial arc. So you will get some knotted annulus in there, but we don't change the ambient space B3 bore. So that's why we can change you will get the new embedding for the surface, but we don't change the ambient space. Okay, so here, to just indicate the surface, then you will get the new surface. We call that the sigma k. So that's the rim surgery. So we call that. So now later.
So to make a long story short, what you do is you take out this annulus, and then for this fiber part, place this by the trip knotted portion.
Right. Yes. Just simply just knotting the annulus. That's the operation. It looks like complicated, but
I don't understand what I can follow.
Right. Yeah. Just geometrically, just that's a simple picture. Yes. Yeah. Okay. So now I'm introducing one more operation. That's just a variation of the rim surgery. We call that a twist rim surgery. So what is a twist rim surgery? This is also you can change the embedding of the surface, but the same situation, exactly same situation. What do you mean by the exactly same situation? Well, we take the surface and then take a non-separating curve and then take the meridian of that. That's the rim torus. We'll choose a rim torus, but we do change the gluing map. So here, take the rim torus. But here, gluing map is a little bit different. So gluing map is, we put the one more operation a little bit. You can change a little bit more if you want, but actually we did that too. But in this talk, we're gonna just concentrate on the just twist part. So boundary of a normal disk, we have to always identify with the longitude. And this one, meridian of surface, identify meridian of the knot. But the alpha factor here, this alpha, this curve identify with S1 for the rim surgery, but we do one more operation there. Here we do and put the M there. What do you mean by that? Well, it's going around this S1 factor. We're also wrapping around M times here, M times, and wrapping around the meridian K2. So just geometrically, we have to think about the isotopy, but when you, here in this case, rim surgery was, here trivial arc was replaced by the knotted arc, right? And then what's a twist rim surgery? We do the same thing, but it's going around alpha factor. We do the rotation M times B3 bore. So we put some rotation happen on the boundary. Okay, so because that's why the twist rim surgery, M twist in this case, if you put the M times around the meridian. So we just add one more operation like in here, the rotation happening. So if you know that somehow the Zeeman's construction like twist span knot in knot theory, so in the three-dimensional case we have a knot, and in S3 we can produce a two-dimensional knot in S4. How can you do that? Take the knotted arc part and just swap it. Then you will get the two-dimensional sphere. Just like when you have a just knot there in the S3, you put the just swap that, then you will get some two-dimensional knot, and then produce the S4 later.
Swap or rotate?
Just swap it.
Swap is changing.
I mean,
Rotate.
okay, rotate. Okay. So then you will get the two-dimensional sphere. But that's the span knot. That's the Zeeman's idea. And when you rotation here, we also rotate the M times meridian of a knot. That's we call it a twist span knot. So that's the same idea happen in the twist rim surgery. So anyway, so that's the way I discussed about two operations, the twist rim surgery and rim surgery.
Why do you need non-separating curve? I mean, it seems like you can do the same thing on this.
Yeah, right. If you do here it bounds some, here's the disc there, then remember the torus was this one times some meridian of the surface. That torus is homologically trivial then. In that case, remember that the diffeomorphism type to distinguish the Seibovit invariant, we need the homology of torus, the homology class of that. That is trivial. In that case, Alexander polynomial is trivial. And then the Seibovit invariant is not changed. So that means we cannot distinguish the diffeomorphism type. So that's why we need a non-separating curve. Actually, that's good. That's a good point. Okay, so then let me discuss about the construction of the exotic surfaces in full manifold. So there is some result using these operations. First, so Fintosh and Stone, they use the rim surgery. The case X is simply connected, and the complement of surface is trivial case. They use the rim surgery, and then they showed they are topologically equivalent. That's they produce a new surface, but smoothly they are not. So they use the Seibovitian computation. Just I mentioned it relate to the Alexander polynomial. So that's the smoothly knotted. But they cannot extend the non-trivial case with the rim surgery. But if you use the twist rim surgery, you can do this. But let me mention the another construction a little bit. Fintosh is also interested in the knotting algebraic curve. In CP2. Why he was interested in this problem? Well, so he used some knot surgery too, but he chose different torus. There was the not rim torus, but he used knot surgery again. So here, if you have a smoothly embedded surface in CP2 with the pi 1, complement of that surface is cyclic case. He constructs another surface. He he changed the embedding of that, and then they make smoothly knotted. So this one is related to the time conjecture. What is the time conjecture is, this one was related to the genus of a surface. Just I'm gonna just mention about the only CP2 case. So if you have a smoothly embedded surface in CP2, and then that homology class is represented by the D times H, that's a generator. And CP2, second homology class. Then what's the genus of this? This one is always greater than or equal to D minus 1, D minus 2. So, the algebraic curve has a minimum genus, so which meaning is algebraic curve.
That's a time conjecture.
Yeah. Algebraic curve minimize the genus. As you can see. So from this fact, time conjecture was proven by like Kronheimer's job, let's over now. So it produced some question like a Kirby problem. Then any smooth embedded surface in CP2, they represent homology class exactly D times H, and also they look like exactly algebraic curve. So the complement of the G mod D, and then also the genus of this surface is exactly same as algebraic curve. Then is this really algebraic curve? Smoothly isotopic to an algebraic curve.
This fundamental group condition, the condition CD, is this a necessary condition for algebraic curve, or?
Yeah, this is a necessary condition because algebraic curve has such a property. If you take the algebraic curve in a the complement of that is G mod D. So
We don't calculate fundamental.
okay. So for topologists, maybe the algebraic geometry is, that's fundamental to you, but we are not.
H1. Not very interesting.
Okay. All right. Anyways, for topologists, fundamental group is not fundamental. So we do care about that. So some surface, smoothly embedded surface has such a property, then can you say this one is really algebraic curve or not? In that case, the actual answer is no. For the degree greater than or equal to 5, the Financial answered. We're using this construction, so not all is greater than or equal to 5 actually. He showed that. But here the open question was, but his construction here, the surface classification
So
for
those
the
two are homeomorphic.
not. That's the question actually. That's the open question.
Whether they are homeomorphic or not.
They didn't know that. So here, so the topological classification of sigma prime was not unknown. So they are homeomorphic or not, they didn't know that. So actually we'll show topological classification. We reserve that this problem later. Actually they are homeomorphic. We can show that later.
But his result is they are not different.
Not diffeomorphic. Yeah, if you take the algebraic curve here, the basic idea is like to answer this question, take an algebraic curve So using his operation, he changed the embedding. He get the new surface like that.
But that's not algebraic.
Right, but this one is not algebraic. Okay, but this surface do have such a here these properties. Exactly. So that's the idea. So later we can. I mentioned in the twist rim surgery. What's the advantage than twist rim surgery case? Well, so we do with a more general case. Take the simply connected manifold, and then if the surface sitting here, and then here the group complement of that surface is cyclic case. Using the twist rim surgery, we can produce new surface. We put the M there because we put the M times, twisting happens, so that's why we call the twist rim surgery. So you got the new surface like this, and then we can show this one is smoothly knotted, so not diffeomorphic, but topologically diffeomorphic. We show that.
What is X?
What is X?
Arbitrary four manifold.
So that's the arbitrary four manifold, simply connected four manifold, any four manifold. It could be CP2 also. So that's why maybe you can, here using this one, actually you can go back this Kirby problem. We can answer more. So this is answer for no, you can show D greater than or equal to 3 using the twist rim surgery. So if the only sphere case, if the D equals to 2 or 1, the surface 2 or 1 is genus is 0, so sphere case, that's the left. Remember the construction of the twist rim surgery, we chose a non-separating curve, also genus was positive, isn't it? So otherwise we cannot distinguish the diffeomorphism type by the Seiberg-Witte invariant. That's why we cannot deal with the D equals 2 and 1. So, and also, just mention here, also we can show financial in the example here, construction of the surface. We can show the topological embedding of this one was actually standard. Okay?
Very naive question. Is X supposed to be something like less compact?
Yeah, of course. Yeah. Close manifold. We always, assume close. Yeah, in four manifold topologists, usually, assume the closed four manifold.
There are
Yeah.
very, very small numbers.
Oh, yeah, I should care about that. Yeah, but I'm just naive now. All right, so then, not just in a cyclic case. Actually, we can extend this question to the any arbitrary group too. So here we extended this problem to the arbitrary group case. So here the question is, first thing, can you construct some surface? You are using the twist rim surgery. Can you construct some surface with here interesting group there? Sometimes we could, so here, the complement of that surface, the fundamental group of that, because sometimes the surface knot group, just follow, analog to the knot group in three-dimensional case. So surface knot group. So we do care. Remember here we just introduced some operation, twist rim surgery. So we get the new surface like that. First thing, we do care about what's the surface knot group of this new surface. if this one is even the surface knot group is different from the original one, easily you can distinguish that. This embedding is changed. You don't have to think about some topological embedding, or even homotopically, even it's different. So that's the first thing, first thing to distinguish of them. So first thing, you have to think about the fundamental group. So that's why. And then we have to think about the topological embedding of this surface. And then what's the smooth embedding of this? Well, topological embedding, you remember that we want to construct the exotic surfaces. So which meaning is topological embedding should be preserved. So it's actually based on, the idea is based on some S-cobordism theorem. And then here, smooth embedding actually distinguished by the Seiberti invariant. So for the surface knot group, so application, this one is actually application of twist rim surgery. So twist rim surgery can produce interesting surface knot also. So we're gonna talk about the construction of surface knots with the interesting knot group. And then you might also, you can knotting this surface again using the twist rim surgery again. Okay, so first thing, how can you surface knots? How can you get the surface knots here? Well, you can start with a pair. Here the X is simply connected. And then here original surface is sigma D. And then do the twist rim surgery. So this surface, we produce a new surface there. So what happened to the knot group for here? So we investigate the knot group of this new surface. Then for any knot, okay, if the M and D, here M was the number of the twist, and then D was related to the original knot group there. So if the M and D, that's the relative prime, then actually the knot group of this new surface is not changed. And another interesting fact here, then what happened to when they are changed then? So here, if the M and they are equal to each other, then this surface has an interesting knot group. It turned out like related to the fundamental group of a branch curve. Default branch curve over K, and then action on here, semi-direct product. Is that right? So the notation is right, or? Yeah. Is that right? Okay. So sigma D acting on here. So it looks like this. So each case, you can make some story there, but here I'm going to talk about this part. Remember that we want to construct some interesting surfaces with an interesting knot group. Then here, look at this. Here, this surface has this knot group here. Depends on the fundamental group of the branch curve. So according to the what fundamental group of the branch curve, we will get somehow the interesting knot group in here. So let me write down. How much time do I have, by the way? 5, 10. Okay.
Actually, it's not.
Okay, then maybe 10 minutes. But if you if you are not bored. Thank you. All right. Then I'm gonna list some of them. Here the question is then what group can be the surface knot group here? So what finite group can be obtained by twist rim surgery? So let's take the D equals 3 first. And then I'm going to take the K is trefoil knot. Then what's the threefold of the trefoil knot? Fundamental group is, actually that's the Cottonian group. So probably maybe you can, using this, in CP2 case, take the algebraic curve. So sometimes we call this a degree D curve. So here, if you take the degree 3 curve, which is algebraic curve, and then the surface knot group is sigma 3, then we call it that's the degree 3 curve. So in this case, degree 3, which meaning is that's the torus. So remember that the genus was, that's the, if the D equals 3, that's the 1, so that's the some torus there. And then if you modify this surface using the twist rim surgery, using this trefoil knot, and then take the 3 twist rim surgery. Then, according to that, this proposition, what's the knot group of that? That's the Cottonian sigma 3 there. So, and then if the D equals 2, take the some 2 bridge knot, then fundamental group of the twofold of 2 bridge knot. I think that's the length space. Yeah. So it's a length space. So because that's the length space, the fundamental group is the sigma p. And then again, you might think about the degree 2 curve here, and then you will get the that's the degree 2. Then if you modify this surface to twist rim surgery, then knot group will be actually sigma p, and then semi-direct product sigma 2. That's the dihedral group. So like that, you might construct interesting some knots, surface knots using suture in the twist rim surgery. And okay, next question is, okay, so using the twist rim surgery, you will get the many surfaces with the interesting surface knot. Then, can you get a exotic surface with the here? Can you modify these surfaces again, and then can you construct such exotic surfaces from here or not? So the answer is okay. So we can do that here. We do the twist rim surgery again. Somehow that it says iteration of a twist rim surgery. Remember, we did the twist rim surgery. Actually, the twist rim surgery. And then we do the one more, modify again, using the different knot, using the different number of the twist. So maybe you can compare two things, and then you might get the exotic surface with the same knot group. Okay. So probably it's maybe I should mention about the topological embedding of the surface and the smooth embedding of that. So in 5 minutes somehow. So okay, then how can you distinguish this new surface and with this? So I will make the more general situation like that.
When you do that twice, you take a non-separated curve, right? It's can they intersect or they are?
No, actually,
not.
yeah, that's the actually point. When you take the one more twist rim surgery, that curve, non-separating curve, that should be parallel. Somehow, using the you have to think about some fundamental.
Parallel to the original.
Yeah, parallel to the original one. Yeah, that's the why do we need that? Well, because of some. Remember, we want this one as some surface knot group is preserved as this, and the topological embedding should be equal but smoothly knotted. But when they are really the preserved for the fundamental group, that the curve should be parallel. Actually, we need that condition
So
later.
in other words, you are doing one surgery, and then on top of it, you are doing one more.
Right. Yeah, that's the geometry picture. Simple geometry picture with some knot in the annulus, K1, another one, K2, something like this. Okay. All right. So here, topological type of sigma j of m. How can you then distinguish the topological type of the surfaces obtained by the twist rim surgery? Here, the simply connected. We assume that now this one is somehow the general group like G. Okay, not just this simply not cyclic group, because we already saw that some example can give some more generic group, so we can assume that. And then in that case, when they this one is topologically preserved, here is the result. So if you do the twist rim surgery, you will get the new surface. group, which meaning is, as cobordism theorem hold. So like in a cyclic group and a finite group, something, there's many good groups contained here. Okay, so here they look at the conditions. It looks like a very complicated, but actually it's not. Here, ribbon condition, ribbon meaning is, let's go just this before 4 ball. Here the knot J on the boundary, that's S3, it bounds some ribbon disk in here. So if you take out the small ball B3, then actually you will get some cobordism between on knot and then this knot. So using such the cobordism, actually we can explicitly construct as cobordism here. That's why. And why do we need this condition? Default cover, branch cover is homology S3. This is related to Whitehead torsion. So to be the Whitehead torsion is defined on the just acyclic complex of the what is it called? That's a covers pair. So that to have such a thing, then we need the condition. Why the MND the relative prime? Well, because this one is knot group was preserved for the MND relative prime. So knot group is preserved. So to complement of that, we can construct some explicit cobordism. Then you can show this is topologically trivial. And then remember, I'm not gonna because time, so I'm not gonna write down. But here I didn't say that G is a good group. If the G is a cyclic group case, actually we don't need such a condition. We don't need a ribbon knot. We don't need such a homology conditions there. Only we need this. Because this one is actually the related to the surgery obstruction. For the surgery obstruction for the cyclic group case, surgery obstruction sit in the wall group. So wall group of the ZMAD cyclic group case are always 0. So obstruction is always 0, which meaning is we can always construct a cobordism and then make that this one is the trivial. So cyclic group case is much simpler. And smooth in the embedding case, why this is smoothly knotted of this? Again, same thing. To compare two pairs, take out the complements of those surfaces, and then take the cyber-width invariant of them. Then, if you compare two things, actually this one is expressed by, roughly speaking, original 1 times Alexander polynomial of that. So if the Alexander polynomial is not 1, then we can make somehow choice of the knot. We can make the smoothly knotted. That's the basic idea. Okay, maybe I should stop here. Yeah.
Excuse me, I don't understand what you are doing here. So you said that you have rim surgery 1 time, and you take another rim surgery.
Yes.
And then you want to compare them.
Yeah.
And then you have, are there anything between what you're saying and then what you said on there?
Yeah, so this one is, let's take this one is general surface sigma again, the notation. And then here, I show the more general fact. Now this is G. Yeah. That's why if G is good group, then we can say this one is pairwise homomorphic. Okay.
Can you get any general relation between this one
Yeah.
and you start from X to sigma J?
Yes.
So X sigma Kj in terms of X sigma K and X sigma J? Because it looks like you are doing...
Okay. Maybe a little bit confused, maybe. So up to here, I just want to show the existence of the some surfaces with the non-cyclic group, non-finite group using the twist rim surgery, and then it should be like this, okay?
I understand, yeah.
Yeah, and then the more ignore that, whatever the construction came from here, when you have such a surface with the G good group as a surface knot group, then we can always show their topological,
I see.
yeah, that's the standard. And then smoothly knottedness coming from the somehow cyber-Bethe invariant computation.
So once you take the rim surgery and the knot group is good enough,
Right.
then you take more.
Yeah, more.
method.
Yeah. Actually, if you do the one, yeah, cyclic case we can make that, but it just in another application you can use the several times you can do the rim surgery, then you will get the more interesting surfaces and then make the exotic as well. So that's the idea.
Do you have any questions? Okay, thank you. Thank you.